Hello, everybody. We're going to continue to introduce to you guys the third section of 13, chapter 13. So maybe
Yes,
I think
Loki.
last
No, Loki. Good morning.
good morning. Oh, okay. Shall we start? So
Okay, Loki.
okay. So last time we talked about plane motion, differential equations of motion of rigid body. We know a rigid body will have different kind of motion, maybe translational movement, maybe rotation around the fixed axis or fixed point, right? And another one in the plane motion. So actually, we have finished the subset of plane motion. We know its formula will be first two is this. So if we select the mass center of this object of this rigid body, so we have the theorem of center of mass. So we will have MACX, right? So d squared f dt squared. There's mistakes. Should be MACX equals sigma fxi. And MACY equal FYI, right? Another one is, so you can look at this right rectangle here. GC is mass moment inertia of this body around its mass center. So it's GC. And the double dot theta actually is angular acceleration. And all the external forces, its moment, the sum of the moment to the mass center C, right? So actually, last time we stopped here. We just talked about this example and time it up. So today we'll continue to finish this example. Then we'll move to the new one. So let's say a circular homogeneous wheel of mass m and radius r. So actually, from this first sentence, we can denote that actually its mass moment inertia of this wheel will be Gc equal half 1 mr squared, right? This wheel is placed on a plane of inclination angle phi. So this slope has the inclination phi, which is the intersection angle with the horizontal line, right? Under the action of gravity here, mg, it starts to move. So it starts to move, assuming that the coefficient of static and kinetic friction are F and F prime respectively, and neglecting the rolling resistance. Let us analyze the motion of the wheel. Actually, I think this example is quite typical because first, I think you see where this wheel move along this slope is in motion, right? Because rotational motion component and the rotation component, right? So we will use the differential equations about motion with body to give the relationship to find its force and motions relationship, right? So you guys can hear we give this coordinate system. So this is x direction and y direction, and the origin O placed here. And we should consider F along this direction, which is opposite to the movement of the center C, right? So after this, you guys can look at the solution together. With the wheel, the free body diagram. Actually, at the first part, static of this whole course, we have talked about the free BD many times. The so-called called free body diagram actually used to do the force analysis, right? So we can see this wheel, it will here have a support Fn and its gravity mg, and another force will be the friction force F. Maybe this force F is static, maybe it's kinetic static, because we should discuss that. So here we have two coefficients, which is static friction, another is the kinetic friction, right? And motion analysis diagram, actually we can use MAD to denote this, also shown in this figure. So it's very easy to figure out. Wheel will have a motion from high position of the slope to the lower position of the slope, and at this process will it also have a rotation, which is the typical plane motion, right? So according to our reference coordinates x or y, so we will have, because this y, because this wheel will move along this slope without jumping, so it always true ACY equal 0, right? It's always true. So we will have MACY equal 0. There is the equation here. No? So MACY, because ACY is 0, so here is 0, to equal sigma FY, right? Just like this, just like this. So along this direction, so we have Fn minus what? Because here is phi angle, and we can easily find actually here is another angle phi. So we can elongate this f into here, right? So we can easily find actually sigma f will be what? Will be Fn minus mg cosine phi. So we will have this. So that is Fn minus mg cosine phi, right? So this will be 0. So we can easily find Fn will equal mg cosine phi. And another one, ACX is AC, right? So because when this wheel is rolling along this slope, its mass of center C, its trajectory or path will always parallel to this line X, right? So ACX, because it's our coordinate, it always equal AC, right? It always equal AC. So MAC means MACX. So you guys can look at the first equation. MAC should equal sigma FX. So we have what? MD sine phi will along this direction of X. And the minus F, because we assume that this frequency F will along this direction. Try to resist its move from high position to the lower position along this slope, right? So that is ACX equal AC. So we have MAC equal MG sine phi minus F. The final one is about the differential equation of the plane motion. This GC double theta. Here we can just write as GC alpha. Here alpha is angular acceleration alpha, right? So we have GC alpha will equal all the external forces. Its geometric sum of moment to point C, which is its mass center C. So we can find here, because MFN and MG, its action line will through this axis, right? So this Fn and Mg will never have moment to point C, right? Never have moment to point C. So only have F. F will have a moment about C, which is along the same direction of alpha. So we have GC alpha equal FR. why this part is positive? Because FR, this moment direction is consistent or the same with alpha. If we assume alpha will along the opposite direction, then we will have to give a negative sign here, right? So actually, according to our analysis, we have these three equations. Actually, in the plane motion related body, it's three differential equations, right? So we will try to, here I means the same thing of GC, because maybe 20 years ago, when I was a college student, when I studied this course, at that time, we use this IC to denote the mass moment of inertia. Actually, the same thing, right? So after we have these three equations A, B, C, we should do some discussion. Why we should give the type of F here, right? So please, you guys, we just consider two of three assumptions. So one is assuming the surface of contact to be totally smooth. You know, this is the ideal assumption. So if we assuming the surface of contact to be absolutely smooth, then we get F equals 0 because there will have no frictionless. So you guys can find from here, we can find if F is 0, then alpha equals 0. That means this wheel will have no rotational motion component, right? And here F also is 0 means our AC will just equal D sine phi, D sine phi, right? And alpha equals 0 and omega will always constant because it's from rest to start, maybe it's always 0, right? Because the wheel moves from rest, 从静止开始运动, right? So the wheel just slides downward without rotation. If this assumption is true, the wheel, the body actually not plane motion, actually it is a translational movement, right? So actually we can look at translational movement to be a special case of plane motion. Just as we also can treat as a rotation around the fixed axis, also is another special case of plane motion. So first assumption. Secondly, we assume that the surface of contact is rough enough. So what it means rough enough? That means if this contact surface is rough enough, then the contact point will have never a relative moment. That means this wheel will have a plane motion, and this contact point will be its instantaneous velocity center. You guys to remember 顺心, right? Which means our AC will equal R times alpha. Why? Because if this surface is rough enough and there have no relative between this contact point and the point on the slope, and the slope is never move, so we will have the velocity of mass center C will be Vc equal omega times R, right? Do you guys still remember actually the middle part in kinetics we have learned this is instantaneous velocity center 顺心. So we do the derivative calculation both sides of this equation. We will easily have AC, right? Because omega is derivative will be alpha R is. So that's why we have AC equal alpha R. So if this case is true, then the wheel will roll without slipping. 纯滚动. You can still remember we have that this terminology 纯滚动. 纯滚动. That means the contact point never has relative movement between the wheel and the slope. So we call that a pure rolling. So that is 纯滚动. So we will have a complementing equation that is AC should equal R alpha, right? So if AC equal R alpha, so we can find because DC we know it's a half mr squared, and we can use this find the relationship between alpha and F, right? And from here we also have AC have relationship with alpha, so we will find the final result, right? So this is the second assumption. Because the next page, not the continue page, because we have some page missing here. So maybe I will just tell you guys the third assumption is, if the surface is not rough enough, that means this point and the point of slope will have some kind of relative moment. Then the friction F will change into kinetic friction, right? So this time, because the second one is rough enough, we will have the friction F in the second assumption. If the surface of contact is rough enough, it means the magnitude F have have no relationship between Fn, right? It's just because of this equation we will find its magnitude, right? But if we assume the surface is not rough enough, then it will have kinetic friction. So this time, AC will equal R alpha will not true, because this contact point no longer is the instantaneous velocity center. So this time we'll write F it just equal what? Equal F prime times Fn, right? F prime means it's kinetic friction coefficient, and Fn is always true. Fn will always equal mg cosine phi, never jumpy, it never jump. So AC always equal 0, right? So this is the third assumption. I will not finish all the detail. You guys just through this example to have a deep understanding about differential equations of plane motion related body, right? So this is the case. And we should look at another example, because this example is a little bit difficult. So I decided only introduce to you guys just the first one. So let's say you guys can find let me find sorry. Let's say this another example. So this example, we have two circular homogeneous cylinders. We can see which means we can see from this picture, right? So we have two circular homogeneous cylinders at here. You can find both are of weight P. So this wheel is the same to this wheel with the same weight P and the same radius R, right? And inextensible string, so between A and B have inextensible string is round on the cylinder A. The other end of the string is round on cylinder B, right? So neglecting the mass of the string and the friction of axis O, let us determine, we just consider the first question, the acceleration of center of mass of cylinder B when it falls. So you guys just follow me. Look at this picture. It's very easy to figure out that the first cylinder A, it will have a rotation around the fixed axis. right? And this cylinder C, because it not have a fixed axis, so it will have a typical plane motion. So it maybe it just a downward movement along this inextensible string, and at the same time, maybe it also have some the wheel move along the inclined slope, right? Not like this. That means this one has a fixed rotation around the fixed axis, and this one will have a plane motion. So how to get the acceleration of the center of mass of center B when it falls? So since it have a plane motion, we should do its force analysis just like this, and then we should use its three differential equations, because the three equations will give the relationship between the acceleration and the forces. So here, let's see the solution. Let's see the solution. So we should consider A and consider B. So for A, we have FBD and MAD shown here. So FBD means free body diagram. That is, we use this terminology to denote that we use this FBD to give the force analysis of this cylinder A. Because here we have a pin, right? So it will have two directional constraint forces, which is Fox and Fy. We also have its weight, P, along the vertical direction, which is opposite to y direction, right? And if we think we cut this ring off, then it will have a tension force here. So please remember, this ring only have a pull function. It only can provide tension forces. It never push, right? It never push. You cannot use the rope to push something move a little bit, right? You can only use the rope to pull something to move along your tension direction, right? So this is the FBD and MAD of A. Also, this is the MBD and FBD and MAD of cylinder B, right? So here, actually, this T and this T will be a pair of action and reaction forces. Let us assume that in this cylinder A will have angular acceleration alpha A along this CW direction. And this string will downward movement. So this plane motion cylinder B will move along this string, and at the same time will have a rotation around the mass center C. We also assume that its direction of angular acceleration alpha B is the same direction of alpha A. So here is the FBD of cylinder B and MAD of cylinder B, right? So this is the motion, and this is AC means is here acceleration of is mass center C, right? And the force analysis is very simple, just is weight P and the tension force T. After we give these two cylinders is MBD and FBD, so we can give the equation respectively. For this one, we will just use the angular momentum, principle of angular momentum. That is dLO dt will equal sigma MOF, right? So here, dLO dt, because for a body which have a rotation around the fixed axis, so its dLO dt just equal GO alpha. So we have here half PG, actually the M R squared is it's GO, right? It's GO, GO, and alpha A sigma F, right? Sigma FO. Because you can find f of x, f of y, and p, you never have moment 2.0. So only have this tension of t, it will have moment 2.0, and its magnitude will be t times r. And this moment's direction have the same direction of alpha a, so we have this. Then it has G O alpha A equal TR. Can you guys understand this? It's not difficult, right? Then we take cylinder B as the object to be investigated. The analysis of force and motion are also shown on this figure. So we can employing the differential equations of plane motion for raised body we have here. So let's see this is the T prime, or we can just use T. So we also have half PGR square alpha B, right? So this is rotational part, right? So we have half mr squared is GC of cylinder B times alpha B will be the action forces in moment sum 2.c. So once again, because P will have no moment to C, then we only have T. And this time T times R also have the same moment direction with the direction of alpha B. So we have half PG R squared alpha B equal TR T prime. Actually, T prime magnitude will just the same of T, right? Another is this. So actually, this is 质心运动定律, a momentum principle of mass center, right? So because we assume that when this wheel downward from high position to lower position, it will have translational moving part, just because the downward movement of this string. It also have another independent rotational component because it's self rotation around axis C, right? So we assume that it have AC always along the vertical line. So we have PG is mass of this cylinder B times AC should equal sigma sigma FC, right? Along this direction. So when we write like this, that means we assume along the direction of AC will be positive, right? That's why we have P, because P have the same direction with AC, so P is positive. And our T prime here opposite from this AC direction, so we will measure T prime, right? So until here, we have three equations. We should try to give the solution, but before that, we should know we should give the relationship between wheel A and wheel B. Actually, its relationship is this: AC equal R alpha A plus R alpha B. I think this relationship is difficult for you guys to understand. I will try to explain this to you. So I think we can try to understand this relation from two methods. The first one is motion superposition, 运动叠加原理. I think I have mentioned this 运动叠加原理 many times. Because we know this cylinder B is plane motion. It will have translational motion component plus rotational motion component simultaneously, right? But we can think these two motion components it happened successively, not simultaneously. Then it will easy for us to understand. So let's say the first translational moving in, because this wheel is rotate along this direction, so this wheel will move downward with its velocity will v equal omega times r, right? And the second, after some time, it move from one position to another position. Then this string will stop here. And at this time, this cylinder will have some angle of rotation around point C. So that means these two motion components, although actually happen simultaneously, but we look at they happened successively. So we can see actually this VC will have two parts. The one part is move along this string, which is omega A times R. Another one is it self pure rotation around C. So it VC will just equal omega B times R because this contact point will also be the instantaneous velocity center. That means from this so-called motion superposition, we can find VC actually has two parts. One part is omega A times R. Another part is omega B times R. So when we write this here, so the first method motion superposition, we will have VC actually will equal omega A R plus omega B R, right? So when we do the derivative calculation from both sides, we will either have AC just equal alpha AR plus alpha BR, right? Alpha BR. That's why this is true. That's why this is the first method to help you guys understand. We also can use the second method. Do you guys still remember what we have learned the complex motion and complexion? So we will have VA here. Actually, the VC we try to figure out. It will equal VE. We call that transport velocity, and VR, what is relative velocity. Here we come back to this figure again. When this cylinder B have plane motion downward, actually it can be treated as it have transport velocity just equal the velocity of this string, and the velocity of this string will just equal omega A times RA, right? Here we will have omega A times RA because R is the same. And the relative is we can, if we are sitting on the rope, we can look at this wheel. It's more like a wheel have pretty rotating along a fixed surface. So it will rotate like this. So its relative movement will induce this C also have another relative velocity VR is omega B times R because this contact point will be instantaneous velocity center of this cylinder B. So once again also equal omega B times R. So I just introduced two methods to help you guys to understand why we have this relationship. And from this equation and this equation, you guys can find this part and this part is equal and T equal T prime. So we will easily find actually alpha A equal alpha B. Then we can find the final answer in alpha A equal alpha B equal 2G over 5R, and AC, because we can find actually it equal 2 times 2R alpha A. So we just time 2R, so eliminate R, we have a 4 over 5G, that is AC. See, this is the second example of this differential equations of plane motion related body. So we will ignore other example and other sub questions, and we just move to the second part. So here we will quickly talk about the rotation along the fixed axis. actually, before we talking about this topic, we have used this, So because A actually is the rigid body who have a rotation around fixed axis O, so here we already use this equation. So for rotation around, we can find actually its differential equation also is 3. The big difference from the plane motion rigid body is that the rotational equations will be GO, that is its rotation center, not GC, not its mass center. That's the difference from the plane motion rigid body. The other things are the same, right? So let's see. Rotation of rigid body around the fixed axis O was described here. So here a lot of kinetic information. You guys should very familiar with that. So assume we have this alpha, maybe we have this omega, right? Maybe this direction, maybe this. So for me, I'd like to always assume that omega have the same direction of alpha, right? And if this C is mass center C, so we will see actually AC have two components. It's quite easy to use natural coordinate system to describe its two opponents. So that is so-called anti-coordinate, right? That is, we can write as AC actually equal what? AT plus AN, right? I hope you guys should very familiar from this. So AN will equal omega squared times R. This R is the mass center C, is the distance to the rotation point O, right? And AT will always equal R times angular acceleration alpha, right? So we have AT here, we have AN here. Then we can give its equations. So we have drc dt squared means actually the MAC. So actually this is the principle of momentum about mass center C, the so-called 质心运动定理. And we can do the projection this equation into x-axis and the y-axis respectively. Then we will have the same thing, which is MACX, right, equal sigma fx, and MACY will equal sigma f, right? The third one will be the rotational motion. So we can very easily give this actually G, I think not GC, should GO, right? We should use GO because this is the rotation point. GO, double theta actually is alpha, right? It is alpha to the equal sigma MOF. So I think this almost the same to the plane motion related body, right? So these two parts will be 质心运动定理, and this is GO alpha equal sigma MOF, right? That's the differential equation of a rotation around the fixed axis body, right? Let's talk about some special cases. If M equals 0, if M equals 0, here means GC alpha, GO alpha will be 0. So alpha equals 0, omega will be constant. So that's the kind of conservation because our LO will always equal JO omega. And GO will never change. It just equal maybe some certain value, and this omega is constant. That means its angular momentum will be a constant vector, right? So the rigid body will rotate uniformly or remain at rest. Because if at the initial time moment, the system is rest, then its omega will always equal 0. Otherwise, if you have uniform uniformly, right? Another one is MO is constant. MO is you have what just uniform rotation. I think it should really have uniformly related rotation, right? It will have acceleration, but its angular acceleration alpha will never change its magnitude, right? So that's the second. Then we will have GO alpha equal MO, right? So actually alpha will equal MO over GO over GO. So the C is MO. Our forces in moment to the point O is a geometric sum, right? So we see that the moment of inertia is the measure of body's inertia concerning its rotation motion, right? So that means once again we can use GO to compare with mass and A equal F. So actually these two equations are very similar. This is the second law of motion. It denotes linear acceleration, but this alpha is angular acceleration. So this is the mass moment of inertia, and this is the moment, and this is reluctant force, right? So that is the thing. We still have a little time. We should quickly see another example. So see in this screen, maybe I should cut it for you guys first, then it's easy to introduce because we can once again to look at the picture. Let's see. So you guess? So in the crane, the widths of wheel A and B. You know, we have two wheel A and wheel B. These two guys all have rotation around the fixed axis O1 and O2 and R2, right? And this inclined angle will be alpha. And consider the circular homogeneous disks are P1 and P2, and their radius are R1, R2. A constant moment M1, you know, so the first wheel will be exerted a constant moment M1, X on the wheel. So this wheel will rotation around the fixed axis O1. Let us determine the acceleration of the load, right? So we can think about that. Actually, when we let this wheel roll, and the string will keep rounded on the wheel, and this weight C will move along vertical line direction. So our task is determine the acceleration of load. So let's see, the weight of the load is P3. So this is P1, P2, and P3. And once again, if we try to tackle this example to you guys look at with me, the FBD and MBD are shown here. So for the second wheel B, its force analysis is FORX, FO2 Y, and P2, right? And here we'll have a tension, and this time we just select this load and this wheel to be a whole system, so we do not give another tension here, right? And for this wheel, it will be action and reaction force T along this direction because spin never pull, always pull, never push, always pull. So always in tension direction. And this is M1, which is try to let this cylinder round, to let this load move upward, right? And we assume its movement is alpha 2 with this direction, and this also along the same direction. But here we assume that alpha 1 along the CCW direction, and this alpha second along the CW direction. It's all okay. It's all okay. You just remember when you give your equation, you should along your assumption on the FBD and MBD, right? So after we do this, we can give this equation. So have 1 P1 over G is M1, right? R1 squared. So this part is it's what? It's GO1 and alpha 1 and alpha 1. So it's equal sigma MO1. So we find, because we assume this alpha 1 will along the counter CCW direction. So M1 will be positive, and this T have opposite direction when T times R1 is another moment 2.0. So we have the first equation. And we should keep consider B and C to be a subsystem, right? So can you guys understand why this is true? Why this is true? Actually, this is, I think, is angular momentum about fixed points. So you guys could look at this. I will try to show you guys. Actually, if we have uh, uh, let me close this and try to explain this. I think maybe we should have a short break. I should give you guys a little bit more time to have rest, and at the same time, you guys can think about that. Why this equation is true, right? We will restart today's second class at 11:10. So it means I will left 3 minutes to let you guys try to think about by yourself why this equation is true. And when we start again, I will tell you why this is true. Okay? So you guys have a rest and think about that. Okay, guys, our time is up. Let's continue. So I leave a question to help you guys can think about why this equation is true. Actually, is we select this load and this wheel cylinder B to be a whole system to be investigated. Actually, we can write angular momentum about fixed point of second, right? So let's see if it run like this. It's run like this. Here we think it will have this alpha second is angular acceleration, and this is move along this direction. So actually we can find the relationship for A. Let's see. We have its velocity is vc, right? And this alpha second is angular acceleration. Let's assume we have its angular velocity with omega second. So first, because this string is intangible, so actually here always have a relationship in our magnitude of Vc. Please pay attention to my explanation. Magnitude of Vc will always equal omega second times r. So because this wheel has a rotation around the fixed axis of second, any point on the wheel spring will equal omega second times r second, right? And so any point on the string also have the same magnitude of velocity. So Vc will be this. That means when we do this derivative calculation, both sides, we will have AC means A here, right? Will equal, because omega second will be acceleration alpha second. And here will be what? R second. So here is a very important relation we will use later. So here we try to write the angular momentum. Do you guys still remember what is angular momentum? So for this one, we have P3 over acceleration G is M3, right? Times is we see this momentum is vector along the vertical direction. We try to figure out its moment to this point of second. So it should times what? Times r second. Right? Why? Why this part is positive? Because we assume this alpha second will be positive, right? So along this direction will be positive. And the second part is because this cylinder B is a rigid body which have a rotation around the fixed axis around O second. So each angular moment will just is GO2 times omega 2, right? GO2 times omega 2. And do you guys still remember? I hope you guys can know some common type of bodies is mass moment of inertia. So this GO2 will be half P second over G is M second, right? And R squared times omega 2. So I will write it here. So this is half P2 over G, which means this part is M2, the mass of the wheel, and times R squared. times omega 2. Omega 2 is the angular velocity of this. So this is the whole system is angular momentum to fix the point O2, right? So do you guys you remember the principle of angular momentum? So we also can write sigma MO2F. That means we want to know all the external forces about this system. Its moment to point O2. So here, the external forces, we have P3 here. So P3 times RR, R second, not RR. But this direction actually is the opposite direction of alpha second. So we have to give a negative sign. And we also have T prime here. So T prime times R2. Its moment along the same direction of alpha 2 here. So we should plus T prime R2. So because we have learned the principle of angular momentum, do you remember? We have dLO2 dt. Right? That's what we so-called the principle of angular momentum should equal sigma MO2F. See? When we do the derivative, do the dLO2 dt, you can find actually this part P3 over G will never change. We see it will be A, and A also can change to A is so here we have this part P, P3 over G will be A, and times R second here for this part. And this part we have 1P2 over GR squared never change. So we have the same. And this omega 2 is derivative will be angular acceleration. It's R2 plus T prime R2. Actually, we just use what we have learned, the principle of angular momentum about fixed point O2, right? So actually, today we are talking about the differential equations about plane motion rigid body or fixed rotation rigid body. Principle of angular momentum, right? This relationship A equal R2, alpha 2 R2 also equal R1 alpha 1 because we can arbitrarily set points. If velocity will always equal omega 1 times R1. So this can also write omega 1 times R1. So it also equal alpha 1 R1. So that's why all these equations true, and we can think about equation like this. So we just these two equations like we have this P2 plus 2P3 over G times A equals this. And what we have to figure out is we try to find in what? We try to determine the acceleration of actually try to figure out A. So our alpha 2, alpha 1 will change into A, right? And then finally we have this. We will have this, right? Finally, we will have this. I know this problem is very hard for you guys to understand, but I still try my best to to do my explanation to you guys. I just hope you guys to have some basic understanding, or at least have some impression here, right? So maybe it should take you a lot of time to understand all the details. But if you have interest in here, maybe you guys can try. Actually, from these and the t equal t prime, we can easily find the final scene. We try to look another very simple example, then we'll move to the chapter 11, right? We should back to chapter 11. So let's say now it tells us maybe we should cut the figure first. Let me cut the figure first. So we have this. So you guys, let's talk about another example. So the homogeneous, we have a homogeneous bar, have mass m and L. Will rotate around one of its end. So I hope you that GO equal 1/3 m squared. Because the long scene, right? So it have mass m, it have length L. So when it have rotation around one of its end, its mass moment of inertia will be 1/3 ml squared. But if when we try to figure out its mass moment inertia about its mass center here, it will be 1/12 times ml squared. See, that's all you should remember. The bar, which is free to rotate in the vertical plane, that we have a vertical plane here, and we keep it rest on the horizontal line, and then we release it from rest. So our hand to hold it. Let it the theta equal 0. Let us find the angular alpha. Theta equals 60 degrees. We just this initial position, which position theta equals 0, and release it. That is freely downward. Actually, it's a swing around this point, right? So we should try to figure out its angular acceleration alpha, because it is the typical raised body have a rotation around fixed point here. So let's go and talk about the solution. Let's talk about the solution. This figure B shows the FBD and MBD. So FBD, we talk about the bar's force analysis. So you guys can find here is the fixed pin. That means it's pinned from the frame and the bar. FOX, FOY. So in many cases, I always assume FOS should along the positive direction of X, but it draw like this. It's okay. It's okay. Okay. So FOX, FOY, and the other external will be the weight of the bar. So it's looking on its mass center C, and the W equal mg. I think this bar force analysis is not difficult for you guys to understand, right? It's very easy to understand. And actually the motion analysis diagram. It's easy. Along this direction, which is CW direction. So our task is when theta equals 60 degrees, try to figure out this time is magnitude of angular acceleration alpha. So when we finish our learning of chapter 11, we should use another method to find this question, this answer. Maybe we will have time to do this. But this we just use the differential equation of related body around the fixed point or fixed axis. You see, we just need to use GO alpha, GO alpha sigma MOF, right? So you only need to write GO is 1. Square alpha equal these two combinations f of y, f of x never have moment about O. So only G. If here, if this angle is 60, right? Now here should be 30, right? Here this angle should be 30 degree. So actually we can do decompose this mg into two components. One along this direction, mg cosine 30, but this action line will through this point O. So this component will have 0 component to point O. Another will be mg sine 30. So mg sine along this direction, mg sine 30, and its arm length will be half L. So we have half L times mg sine 30. Sine 30 also equal cosine 60, right? So that's why. So this is this mg is equal to O, right? We also can think about this method. We can just mg. We draw. We try to figure out some length. Here, 60. So it's D. D is so two methods get the same result. You can easily find alpha, right? So here we have we have G with what, but my question is, if I hope you get can find the y and f of x, these two forces is magnitude. How should we do? So here we just give you some clue. So you guys can try to finish by yourself. So actually, we have a here. So you should try to find its ACT and ACN. But here maybe a little bit difficult to find ACN, but we only alpha. We don't have omega. So how should we get the omega? How should we get the omega? So maybe we should use some method of what we're going to learn chapter 11, right? And I think that the part of the chapter we left the final section part, section 4, the general principle is section part is more complex. Maybe we don't have time to learn this. and principle of angular momentum plus kinetic. We do not learn that yet. So we have to learn first and learn the third principle. Then, if we have time, we can this section is learning. But you know this is the second right? This how to say this Thursday, right? This Thursday we will have the final class. We only have one, so maybe we just the 11th learning, then the whole class will terminate it. Next time maybe I will talk about the final examination to you guys. So here I just want to say, you guys, all you guys, don't worry about the final examination. It will be easy for you guys to finish. I will give you guys enough time to finish that. But before we talk about the final examination, finish the 11th learning. So maybe today we still have 20 minutes. We'll back to the chapter 11. So actually, we have learned one of section of this chapter 11. Talk about the second section of the mass moment inertia, right? So actually, the chapter 11 talk about the principle of work and kinetic energy. Here, kinetic energy in Chinese we call that 动能. 动能. So it means when you have some kind of motion, you will have some energy, right? So energy is 动能. So actually, we try to call this principle of work and kinetic energy with 动能定理. So back to here, the general principles actually should include the principle of momentum, principle of angular momentum, of work, and the kinetic energy. So that's three principles. We only learn two of them. So from here, from now, we should continue to learn the third principle, that is the principle of work and the kinetic energy. Today, we don't have enough time to finish the whole chapter 11. Maybe we should try to finish the first section. So the principle of work and energy established actually another method. Establishes the dependence between the physical quantities describing motion, kinetic energy, and describing the action force, work. So in this chapter, all the force will have some kind of work, and also work will let the body system change its kinetic energy. So this principle of work energy established, we also can use so-called 功能原理. 功能原理. See? It tries to establish the dependence between the physical quantities describing motion, kinetic energy, 动能, and describing the acting force, work. It changes between different forms of energy. So when we finish this chapter's learning, we will have delta T will W 1, 2. Let's see. This is time moment T1, and this is time moment T2. So this T1 to T2, all the acting forces may be work. It can be calculated and do the sum. and all the sum of work will let the body system change its energy. So we have delta T will be equal T second minus T1. So maybe use this method, we can find something. So let me back to this example. I will show you guys to have a first impression of this sort of work and principle. Let's use this example again. Try to give you again how to find omega, because ACN should equal omega squared times half L, right? But we don't know what omega should be, so you guys can find we should equal 0 at 1, but at this time it hold it by hand or another thing actually rest, so T1 will be 0. So let's say when it swing from theta equals 0 to theta equals 60, so this second we should give it kinetic energy because it is a bar have a rotation around the fixed axis. So its kinetic energy will be half Go omega squared. See? We try to figure out what omega should be. So Go, because Go is 1/3 L squared, so we will have 1/6, right? 1/6 because we should times 1/2. So here will be 1/6 m L squared times omega squared. This is the kinetic energy of this bar at this position. And from the position 1 to position 2nd, only weight will have what? Only weight will have some work, will do some work. So we try to, because it's always along the vertical line, so we to find at this position at here, when to this position, let me guess. Sorry. We'll draw a line. So let me change another color. So at the first position, when T1 here, so its mass center C maybe at here, right? Maybe at here, it's C1. And here, when theta equals 60, we call that maybe C2, right? We just need to find these two position, the vertical distance. We just need to find from here to here. So this part actually will be the length of will be half L times sine 60. So that's the work by the gravity force or weight mg. So the work W12 you guess will be mg. Maybe I will change the color into because it's not clear. So it's mg times s. S will be half at 60. See, you can just because T2 minus T1 just equal this, so you can just use delta T equal W12, and you can find actually our this one is known, this one all known, so we can find omega, right? We can find omega. Because this can be eliminated. And the sine 60 will be, we have, let me try to eliminate one L, only have this L. M is eliminated and L just one, so we can here so 6, so we have 3D. 6 will be square root 3 over 2, right? We still have an L here, so we also should L this. Then you can find this, right? So you can find your omega square. You just use this principle of work and kinetic energy, and then you can find ACT, ACN, and you should use the principle of momentum about mass center C to finally find f of y and f of x. So please, you guys pay attention here. Maybe in the final examination, I will let this to be the final one to let you guys to find the final result, right? Maybe it's a little challenging for you guys. After this whole example, we'll back to the learning of 11 chapter 11. So maybe we only have time to finish the first section. Let me talk about the work of a force. We call that 力做的功。The work of a force, we call that the effect of the action of a force will be characterized by using notation of work. See, logical path is first we will select a single particle to be studied, and then we should move into a system of particles. Because the rigid body is a special case of a system of particles, and the body system also is a special case of system of particles, right? So here we do the same thing. First, we talk about the effect of the action of a force on the particle can be characterized by the notation of work. So what is the work? Work is the measure of action of force relative to the path traveled by the point of application of force. So in Chinese, in English, when somebody congratulate to you, well done, you really do a good work, right? You get have this kind of expression, right? 说你做得很好 right? 你做得太好了。Talk about this word is the end of the force. Leave this concept, work or constant force. So here force means because force is a vector, if its magnitude and direction will never change at some certain time span, we call that this force is a constant force. So if an external force F acts on the body, as shown in this figure, and maintains a constant magnitude F and a constant direction alpha. Let's say this action line of F have intersected with the horizontal line with F alpha, which means it never change. The body S from position A1 to position A2, then the work done by the force F, W equal F dot product, dot product. So when we write, because here we use bold letter to show this vector. So when we write, we should actually W, I'm sorry, I will change the color to write again. W not scalar. but F and S we can write as W equal F vector dot product S vector. No, because when we do the calculation of the dot product of two vectors, the magnitude will be the norm of F and the norm of S times cosine the intercept angle which will be alpha. So that is F S cosine alpha. Right? So actually the very interesting thing is if we use we decompose this F, it's quite hard. Actually also can do this. I will draw two lines that use this. So actually we can do the decompose. We can decompose this F into F1 and F2. Right? So you guys can find actually F1 should equal F times cosine alpha, right? And F2 will equal F times sine alpha. So actually it's more like the force done by this, the work done by this force F actually is mainly because of the F1, because F1 equal F cosine. F1 times S. So in other words, it means the vertical component of F second, because its direction is perpendicular to S. So the work of this F2 will be 0. So anyway, that so work done by force is a scalar quantity, scalar vector. That means this quantity only have magnitude, not have direction. The unit of work in the SI units is the joule, which joule. I don't know how to read in English. Maybe joule, right? Actually, joule. The Chinese call this joule. So one joule means a force with magnitude 1 newtons lets the body to move along its direction 1 meter, right? So 1 joule equal 1 newton times 1 meter. Then we'll continue to talk about work by a variable force. So we now develop the quantitative meaning of term work. So with the force F acting on the particle and move along the path shown. let me cut it to help you get done here. Let me cut it here. So here the work of a variable force. Let's say now quantitative work. So in this phase, force F. Our is the particle on the particle and go along from A1 and A second. So when we just analyze the motion of a particle, we will see if we know a particle along a fixed trajectory path, then at some position we can analyze its velocity and acceleration, blah blah blah, right? Here we talk about this force acting on this particle, and this particle has this path of motion. We talk about its force. So magnitude and direction of f may be changed. We have to find appropriate method to find the work of a variable force. So let's see together. Now, do you know R cross F will be the moment of F is point O, right? And from case the product it passes point A, right? And dr is a differential displacement associated with an infinitesimal, that's 无穷小 in Chinese. Infinite small means a second. Very, very small part to study. Why we should do this? Because this, if in small moment, we should assume that because this part is short enough, we can assume that in this very, very short F will never change its magnitude and direction. So that means the work done by F during this displacement, we should very, very small. It's small enough. It may be this A1, this A with another position, maybe overlap together. It's quite small enough. So in this very short length, we consider that F is a constant vector, right? So we have dW. In China, we call that 员工. dW will equal F dot dot product dr, just like this, right? So we have F dr. When we try to get the whole work from A1 to A2, then we should use the derivative calculation, right? So our dW equal F dot dr, F dot dr equal, because when dr is small enough, we can just assume that dr actually equal ds, right? It's a very short part of the path A1 to A2, right? So we have dW actually equal F cosine theta dot ds, right? Dot ds. The results may be interpreted in one of two ways, either as the product of F and the component of displacement cosine theta ds, right? In the direction of force. Or we can say the product of ds and the component of force, F cosine Ft. So you guys should pay attention to here. Maybe you will find this many times. Actually, we call that Ft equal F cosine theta. It is the main reason for the F do the work when this particle have a length s, right? So we use this t to means in China we always call that 切向力. Maybe t means tangent line direction. We also call that is 驱动力. That actually this component force, this force Ft, the reason why there have some work. Then the total work done for this integral calculation. So FA1, A2, F ds. Then we just write F and dr ds into three components. Change into this. It changed into this. So actually, this just tell us what to work and how to find a variable or f it work. But when we try to figure out its result, it should to the type of force acting on the particle, right? So in order to carry out this integration, it is necessary to know the relations between the force components Fx, Fy, and Fz and their respective coordinates or relation between Ft and S, right? If the functional relationship is not known as a mathematical expression which can be integrated but is specified in the form of approximate or experimental data, right? So if we have a relationship, we can just use the mathematical method to find the result. If not, we just depend on experimental data, right? So after I this expression to you guys, we'll talk about different kind of forces with work, right? So we only have time to talk about the work done by special forces, the work associated with weight. You know, weight, weight actually is the gravitational force between the body and the earth, right? Because the earth is big enough, it always have gravitational force to anybody on the earth. So, uh, okay, if the finish small, uh, because we don't have to finish this, maybe we will continue next for today. Okay, uh, next time to use different kind of process it work. Okay, that's all for today. Bye bye, bye bye, you guys.
Bye bye.
Bye
Okay,
bye.
老师再见。
Thank you. Bye bye.
拜拜，老师。
Bye bye.